Double slit problem. Monochromatic light strikes a double slit apparatus as shown. Here's your light. Here's the apparatus. The separation between the slits is D. As a result of diffraction and interference, a pattern is produced on the second screen, and you can see the sine waves there, 3 meters away. Find the wavelength of the incident light based on the interference pattern, and what is the frequency of the light? Then we submerge the whole thing in water. I don't know why, but we do it. N is equal to 1.33. That's the index of refraction for water. What is the frequency of the light in water? What is the wavelength of the light in water? And what happens to the distance between two adjacent fringes in the water? And they're looking for the distance between those guys. Find the wavelength of the incident light based on the interference pattern. We use our double slit equation here. Okay, and X is going to be in this direction. That's X, okay? So that's M lambda L over D. Now, from the graph, where is our first maximum? The first maximum is going to be over here. All right, you might say, well, how about in the middle? Well, that's the M equals 0 maximum. So they want the one that's spread out a little bit. So we have lambda. We have to rearrange this equation for lambda. So you multiply through by D over ML, and that will cancel out all the variables next to the lambda and move them over to X. So we have lambda is X times D over ML. We substitute in our numbers and make sure you convert millimeters to meters. So that's 10 to the minus 3 meters. This is 10 to the minus 3 meters. Then our distance to the screen is 3 meters. That's this distance here, L. L is 3. And we're going to take the first order maximum because that's what we measured over there. So we get 6.67 times 10 to the minus 7th meters. And then if you want to express it in nanometers, because visible light is in that range, 667 nanometers, that's visible light, you would move the decimal over 2 to the right. That would decrease this power by 2. So it would go from -7 to -9, and -9 meters is a nanometer. So here's our answer in nanometers. What is the frequency of the light? Well, we have our speed of light equation. C is equal to lambda F. Divide both sides by lambda to isolate frequency. Put in the speed of light, which is 3 times 10 to the 8th meters per second. And if you haven't memorized that yet, it'll probably stick in your mind. We'll use it so much. And if not, you just look at your table of constants. And we found the wavelength on the previous slide. And again, we have to use meters here. Why? Because the speed of light is in meters, and you need that to cancel out. And we get a frequency is 4.5 times 10 to the 14th hertz. We then submerge the apparatus in water. What is the frequency of light in the water? No calculation needed here. It's the same. The frequency of light does not change when light enters a new medium. The wavelength will change, and the effective speed of light in the medium will change, but the frequency stays constant. What is the wavelength of the light in water? Well, our new wavelength, where we have an index of refraction that is not 1, it's 1.33. It's equal to the wavelength of the light in the air divided by the index of refraction. So we get 501 nanometers. The wavelength in the water is decreased by a factor of the index of refraction. What happens to the distance between two adjacent fringes in water? So let's say we have one fringe here, M equals 1, and here's another fringe, M equals 2. We want to know what happens to this distance. Well, we look at our equation that tells us where the fringes are for constructive interference. It's M lambda L over D. M will stay the same when we compare them because it's going to be 0, 1, 2, 3. In this case, it'll be M is equal to 1, M is equal to 2. So what we can do is compare M equals 1, where its fringe is, to M equals 1 for the fringe when it's in water. What stays constant on this equation? The distance between the screen and the source is the same. The distance between the two slits is the same. And we'll compare it with the same M. Lambda is decreasing. So if lambda decreases and everybody else is constant, then the distance from the center point for both fringes will go down. Both of these will go down and they'll get closer together. So what happens is the distance between two adjacent fringes decreases.